Okay, this was the assignment on the back of the syllabus, and it was really just an opportunity for you to sort of explore some different ideas. Nothing you need to absolutely know right now. You're free to look them up. Some of them are a little more philosophical, so just talking about some of the terms we're going to be using, also vocabulary this year. So, in your own words, describe the difference between a line, a curve, and a cusp. You could describe them also by drawing a picture. So, a line has a constant slope, it goes forever, right? So, constant slope. And then a curve, a curve could be like a lot of polynomials are curves, so they vary in steepness. They go up and they go down, but they're usually smooth, right? So smooth, all connected, changing slope. Parabola could be one. Now a cusp is something kind of like this. A cusp is sort of like a sharp point, but kind of like a curve into a point. So we call that a cusp. And this is actually a function that we will probably study. This is like an example could be like this, the cube root of x squared, or in other words, x to the 2/3 if you want to write it as a rational exponent. Well, what happens is if you plug 0 in, you get 0, but all the negatives are going to have the same value as the positives because of the squared. And the slope, interesting thing here, is when it's going right here to this point, the slope goes to infinity. It's infinitely steep. Another function that we're going to deal with would be like a corner. And a corner, it's kind of similar to a cusp in some ways, that it's sort of this sharp thing. So a lot of curves don't have these things on them. But this would be like an absolute value function, which you guys should have seen before. But it's like a corner. Now here the slopes don't go to infinity, right, like they do here, but here the slopes do make this dramatic change, whereas usually on smooth curves the slopes are all kind of gradually going into each other. I might call this, by the way, a Siegel function. That's not its technical name. Describe the difference between these two statements. Prices of cars are increasing. The rate of change of car prices is increasing. So, prices of cars increasing just means that they're going up. 25,000, 30,000, 35,000. This is just an example, but what's happening here is this is at a constant rate. So the rate is the amount of change. So the rate isn't increasing, but the prices are increasing. The rate increasing would be like, going from 25,000 to 30,000 to 40,000. So now the changes are going up by bigger and bigger amounts. So, and it could even be, even if prices are decreasing, you could say that the rate is increasing. So maybe they dropped 10,000 and then it only dropped 5,000. So it dropped 10,000 and then it dropped 5,000. Well, that means that it's dropping by, or it's changing by a positive amount. Like we're going towards eventually it would keep going into positive territory. So, do all functions appear to be linear when viewed up close? Yeah. Yes. As long as they're, smooth. If you zoom in on a curve enough, on like even your graphing calculator, you zoom in, zoom in, zoom in, and it's going to look like a straight line. So we actually rely on this idea to develop some of our calculus, proofs. We might call it linearization or local linearization. So, but not at a cusp or corner, right? That it can't happen there. Now, it's the exceptions and the weird cases that we actually end up spending a lot of our energy on. Because the straightforward ones, like, all right, they're straightforward. So uh, the exceptions will be interesting. I guess we'll have to figure out how to deal with them. They're sort of the challenge. But on a graphing calculator, I mean, we could do y equals x to the third plus x squared or something. Window, zoom, standard. So here's like a cubic. And if I zoom in, zoom box. So I'll try and zoom in on like what seems to be the curviest part of it also. So, it's pretty curvy. But if we zoom enough on, even where it's curving the most, it's going to start to look like a straight line. Like you can still kind of see a little bit of curve on there, but it's gonna look like a straight line. Which of these functions ultimately grows faster as x increases? So we're going to need to kind of know how functions behave and how they behave relative to other ones. So this is a line which grows at a rate of 10. This is a polynomial, which, raising something to the 10th power does raise it a lot, but doing 10 to a increasing x, this is exponential. And exponential functions dominate most other functions in growth. What is the calculus? So I'll let you, you can find out what you can Google that. But some of these other questions sort of get into it. Was calculus invented or discovered? So this is kind of an interesting way of thinking about things. Like, did someone come up with calculus and or is it sort of underlying in nature and we figured it out, like it's used for lots of natural phenomenon. So is it just there and we figured out how to write notation for it and represent it? Or did we create it and it's just really helpful, so, is it a human invention or is it sort of a natural, sort of result? Who first invented and discovered calculus? So there's a little bit of drama here, but generally we attribute Isaac Newton for being the first to sort of put it together in 1666. But the problem is that he didn't publish his findings until 1693, 27 years later, part of it, and then the full version of it in 1704. So that's like 38 years later. And so that kind of resulted in sort of some issues because Gottfried Leibniz was the first to publish it in 1684. So, but even way before these guys, like, over 1,000 years before this, Archimedes, a Greek mathematician, was really kind of on the verge of it and inventing it. And he was murdered by the Romans, but and his manuscript was lost. It was never really known, and then it kind of popped up within the last 100 years, and people realized that he was really kind of figuring calculus out way before these guys, and we just lost it. Like, so be interesting how much further we would be along in technology if calculus hadn't been lost for a couple thousand years. Because calculus is, the foundation of engineering and many of our technological breakthroughs. Students enter AGHS at a rate of 550 students per year. Students leave AGHS at a rate of 500 students per year. In 2009, AGHS had 2,200 students. At those rates, in what year will our school have 2,500 students? So I think we may have even passed this mark at this point, but so I mean, this kind of sounds like an exponential growth problem, but it isn't. We're saying that they enter at this rate and they leave at this rate, right? So the total amount equals the amount of people coming in a year. We call X, and it says, and then they're leaving at 500 per year. And then you got to add some like initial known value. And that's where we can use in 2009, that's your X value. We had 2,200 students. So we might put a C here for right now and be like, well, what is that value? We say, well, in 2000, we had 2,200 students when X equaled 2009. I mean, this is one way to do it. It's going to be some big numbers here. I think I did it differently before. But why not? Let's just use a calculator. So 2,200 plus, minus 550 times 2009 plus 500 times 2009 equals, so that means that C equals negative 98250. If we say that X is the number of years since time 0, so we have this equation, and I guess we could even combine the 550x minus the 500x, because that would just be 50x. And then we could say, well, how do we figure out when it's going to be 2,500? Well, we set the value to 2,500 and we solve the equation. So we could do 2,500 plus 98,250 divided by 50. X equals 2015. All right. Why is the integral also known as the accumulator? So some of you guys may have seen this in pre-calc, maybe you haven't, but this is a calculus notation that we're going to spend plenty of time learning in the second semester of this year. But if you integrate a derivative, some of you guys is going to go over your head. That's fine. You get the original function. And so if you integrate the derivative, now the derivative is the rate of change. So it's kind of like the slope of a function. But if you keep track of all the changes, then the integral adds all these changes up. So anyways, accumulator, it's about adding up small changes. We also might use it to find the area under a curve, and the way you do it is you slice it. When you add them all up, you add up all the slices, you accumulate them all. Find the average value of a function. So what's the average value? Now the average value is talking about the average y value. Now we could graph this to kind of get a visual on this. This is a line, it has a y-intercept of 3, slope of 2, up 2 over 1, up 2 over 1, up 2 over 1. So it kind of looks like that. And we want to say from 0 to 10. So starting here all the way to 10. What's the average value? And it goes, so at 10, if you plug 10 to this, you get 17. Right? Now, there's actually an infinite number of values on this line between 0 and 10. But the average of them really is just going to be the endpoints added up and divided by 2. That's going to be the middle of all the heights of this graph. Now, in calculus, we learned some other ways of doing this, where we say, well, let's find the area under the graph. And one way of writing that in calculus is with the interval. So we can find the area under the graph, and there's some negative area and positive area. There's 2 triangles, 1/2. This triangle looks like the base is 1.5 and the height is -3. And then this other triangle, I think the base is going to be from 1.5 to 10.5. So that'd be 8.5. So that'd be 17/2, and the height is 10. This is interesting. So we get -9/4 plus 170/4, which is 161/4. Hopefully I've done all this correctly. Let's see. 3/2, 8.5. Seems good. All right. So we get this. That's the area of the positive triangle and the negative triangle together. Oh, this is, yeah, okay. So then we take that area and we divide it by the difference between the endpoints, 10 minus 0. So 1/10 times 161/4. Now I feel like I'm actually messing this up because I think we should get 7. So we get 161/40. So I think I messed something up. Let's see. No. Okay. You plug 10 in, get 17. Oh, the height is 17. That's what I messed up. Height 17. So 17 times 17, I think it's like 289. So then you have 280, which is 140 over 270. And 1/10 times 70 is 7. Until it gives us the same answer. But anyways, we're going to look at some different ways to find these answers. Number 12, true or false, the maximum value of function always occurs at a point where the slope of the function is 0. If false, show a sketch a counterexample. So a lot of times the absolute value, the maximum of a function is the highest or lowest point. And so a lot of times a key characteristic is that the slope is 0. Right? Or the lowest point could be at the slope is 0. Usually it's when the curve changes direction, right? And the curve, when it changes direction, its tangent line is the slope of 0. But, usually this is true for a nice smooth curve, okay? But what about a cusp, okay? The slope here is not 0. Okay, but this is the maximum value of the function. In fact, the slope we would say is undefined. It doesn't have a value because you can't give that a number. In fact, one side's positive slope and the other side's a negative slope, so they really disagree with each other. But anyways, this was just a nice little worksheet to get you to start thinking about some of these ideas. You're not really required to know any of this yet, but this is just to get you to start thinking about some bigger ideas. And we're going to be discussing a lot of these over the course of our whole year.